Hi, I'm Mohammad Farazman and this is a brief video description of the paper displayed on your screen. In this paper, we consider the motion of particles carried by the free surface of a water wave. We consider a unidirectional wave moving in the x direction. The free surface is given by a time-dependent graph over x. This graph is denoted by the function zeta. We assume that this function is known. The position of the particle is given by its horizontal coordinate x and its vertical coordinate z. Since the particle is constrained to the surface and the surface is known, the vertical position of the particle can be inferred from its horizontal position. Therefore, the only unknown here is x of t. What I will describe applies to arbitrary bottom topographies and shallow or deep water waves. The only restriction is that we assume there is no wave breaking, so that the free surface stays a graph over the x-coordinate for all times. We are interested in two quantities. First is the mean value of x, that is the average horizontal position of the particles. We are also interested in the variance of the particle positions. More precisely, we start from a given initial condition x0 and would like to characterize the distribution of the particles after time t. Note that since the surface waves are random, the position of the particle at time t is also a random variable. The ensemble averages are taken over the realizations of the random wave. These two quantities have been studied extensively. In particular, Stokes predicted that the mean particle position increases linearly with time. G.I. Taylor addressed the growth of the variance and predicted that for short times, the variance increases quadratically with time, and for long times, the variance increases linearly. It is noteworthy that Taylor's theory applies more generally to particle motion in turbulent flows. However, in order to derive this theory, Taylor makes a number of simplifying assumptions about the particle velocities. The purpose of our paper is to show that while Stokes' theory holds up, Taylor dispersion theory breaks down for surface waves. We will show later that the main reason for the failure of the theory is the third assumption regarding the autocorrelation of the particle velocities. Instead of making simplifying assumptions about their motion, here we use an exact equation to evolve the particles in time. This equation, known as the John-Sklavounos equation, is a non-autonomous second-order differential equation for the particle position. Note that it involves the partial derivatives of the free surface and the gravitational constant g. This equation was first derived by Fritz John in 1953 for unidirectional and irrotational water waves. In 2005, Paul Sklavounos generalized it to rotational two-dimensional waves. Fedele, Chandre, and myself derived the same equation from first principles. Our derivation can be found in the JFM paper cited here. Our numerical simulations are carried out as follows. We solve the John-Sklavounos equation using a fourth-order Runge-Kudai scheme. The surface waves are assumed to be a superposition of linear waves following the John-Suave spectrum. Here, Ki denotes the wave number, omega I is the frequency following the deep water dispersion relation. Phi I are random phases, uniformly distributed over 0 and 2 pi. The initial conditions for integrating the JS or John-Sklavounos equation are the following. We initialize the particles at the origin. The initial velocity of each particle is chosen to coincide with the linear wave theory. However, it should be noted that our results are not sensitive to choice of initial conditions. Note that the only randomness here comes from the random surface wave zeta. We consider 10,000 waves. For each random wave, we evolve the particle and record its position and velocity at later times. This slide shows our numerical results. The mean particle position grows linearly with time, agreeing with Stokes' theory. The variance of the particle distribution grows initially as t to the 4. For longer times, this growth slows down to t squared. Note that this violates the Taylor theory that predicted a t squared initial growth followed by a linear growth for longer times. In each panel, we plot three curves corresponding to three wave steepness epsilon. We choose the steepness to be small enough to avoid the breaking wave regime. Interestingly, the particle positions and velocities follow a Gaussian distribution. Therefore, the deviation from Taylor's theory cannot be attributed to heavy tails of these distributions. This figure shows the autocorrelation function of the particle velocities. Note that it decays to 1/2 and not to 0. This implies that velocities of particles on surface waves stay correlated indefinitely. This violates Taylor dispersion assumption that these correlations decay to 0. To summarize, we examined the dispersion of particles by random waves. We confirmed the Stokes theory regarding the average displacement of the particles. However, the particle variance grows much more rapidly compared to the Taylor dispersion theory. To obtain these results, we used an exact equation known as the John-Sklavounos equation to evolve the particles. The main reason for the breakdown of the Taylor dispersion theory is that the particle velocities on surface waves do not decorrelate in finite time. Thank you very much for your attention.